This is Group 15 submission for the MAE 152 Winter 2025 final project. We have decided to conduct a series of FEA analysis on a race car created by Anteater Baja Racing, which many of our members are a part of. Here is the MasterCAD and the responsibilities breakdown of this project. My name is Yulin and I worked on the Chelyam of the vehicle. Through the two design iterations of the part, I aim to decrease the max stress and displacement experienced on the Chelyam from the static simulations including impact, bump, and lateral force. A modal analysis was also conducted. The impact case scenario simulates a rock hitting the vehicle from the bottom with 600 pounds of force. Boundary conditions with free body diagrams results shown on table. The bump force scenario simulates a vehicle landing from a 3-foot jump to have 1700 pounds of force applied at the mounting tabs. Details shown on table. The lateral force scenario simulates a vehicle turning at a speed of 20 miles per hour. Common during racing, details shown on table. The biggest stress on the slides from bump force, 337 megapascals, was still within the yield stress of 351 megapascals, meaning no yielding. Through modal analysis, resonant frequencies increased compared to the base design. Since it is nowhere near the frequency in which the engine vibrates at, there is no concern of resonance. The closed-form solutions for the max stress and displacement computed with the geometry values and material properties from SolidWorks are conservative compared to the FEA results. A situation where the part may be exposed to long-term use is the bump force condition. Through the estimated competition and testing usage of the race car, the cycles needed is 10 to the 4th power. Since the max stress computed from bump force is 337 megapascals, this point can be plotted under the SN curve for AISI 1020 to show fatigue is not a concern given the stated conditions.
Hi, my name is Sebastian, and I worked on the upright. For my 3 design iterations, I aim to minimize stress, especially where the mounting tabs for the control arms attached to the upright, as this location is most likely to fail. I performed a braking, bump, and lateral impact load case, as well as a modal analysis. I utilized a braking torque load of 236 pound-foot, a bump force of 1,274 pound-force, and a lateral impact force of 1,646 pound-foot, as specified as performance requirements from the Baja team. I've also utilized fixed cylinder conditions for the given boundary condition, as well as fixing the bottom tab and putting the top one on rollers as another boundary condition. From the modal analysis, we can see that there is no risk of engine vibrations causing any resonance on the upright, as an engine produces roughly between 100 and 600 radians per second vibrations. The first iteration had the highest resonant frequencies, followed by the second iteration, and finally the base. Calculating the closed form solution showed that our calculations were on average less than the stress and displacement values we produced through SolidWorks. Finally, you can see our max stress plotted on the SN curve for 4130 steel. I believe the area most prone to failure is the control arm mounting tab joint due to fatigue over time.
Hi, my name is Daniela and I worked on the rotor. During my 3 design iterations, I wanted to decrease the stress in the cornered fillets where the rotor mounts to the adapter. Because of this, I changed the radius of the fillets to 0.4 inches and changed the whole pattern with the intent to improve heat dissipation and weight reduction. I ran static, thermal, and modal analysis in each of these changes. On the torque case, I ran 2 different scenarios, one where the caliper was loose and the other where the caliper was fixed and clamping on the rotor. Under the impact case, I analyzed the rotor and in the event that the fasteners were either tight or loose. Finally, I simulated a thermal load due to braking under stagnant air and forced cooling air. Both of these boundary conditions were under the assumption that the theoretical heat power were calculated at 6.6 kilowatts. While the change in radius improved the heat dissipation, the whole pattern change did the opposite and increased the rotor temperature by about 150 to 200 Kelvin, hence the negative percent change. Here are the modal analysis results for the rotor. I compare the impact case to the closed form solution I calculated below. I calculated the max stress to be about 1,170 megapascals, which does yield.
Hi, my name is James and I worked on the steering components. In my 3 design iterations, my main goal was to decrease the stress in the tie rod and the rack mount, as these were the components with the greatest stress concentrations under loading. I ran static and modal/frequency analysis. In the impact case, the rack mount is held fixed while the tie rod receives a bump force on its end. In the max steering effort case, the rack is allowed to move and the tie rods are held fixed. In the brake force case, the rack mount is held fixed while the 2 tie rods are pushed in towards each other. As shown, the 2 iterations made a positive difference and decreased the stress. In all 3 cases, the loads were calculated using a steering force calculator developed by the Baja team. There is no yielding. The modal analysis shows that the natural frequency of the rack is not near the frequency of an engine and therefore it is unlikely to be excited under operation, causing failure. As shown by the closed form solutions compared to the SolidWorks, the closed form solutions are much more conservative. I think that a buckling failure is most likely for the tie rod.
Hello, my name is Tiffany, and for this project, I did analysis over a chassis frame for a Baja vehicle. The point of the iterations are to make it so that the stress is reduced and we can make a better performance outcome. For first load case, it is an impact force to the front, where all the bomb beams are fixed while the front takes in all the force. For next load case, it's an impact force to the side, where one side is simply fixed while the other side has force, vertical horizontal to one beam. And the last is rollover, where we put the force on the top of the chassis members while the bottom members are fixed. The next thing we did is a frequency analysis, which you can see here that all the frequency values obtained are reasonable, which is a good sign. For the last thing we did, we calculated as well as found the max stress and displacement from SolidWorks and found the percent error And from the errors shown, you can see that there are some differences, but it's not too significant. Thanks for listening.